exponential decay functions. So our objective is to analyze the characteristics of exponential decay functions. Since we've already talked about exponential growth functions, this section is going to be very similar. So I foresee it going quite smoothly for most of us. Really, the only difference between an exponential growth function and an exponential decay function is it's going to be of that same form. F of x equals a times b to the x. In a growth, basically we look at that base, that b. If that b is greater than 1, it's going to be a growth. If b is less than 1, but also greater than 0, it's going to be a decay. Because we're multiplying a fraction or part of a number a certain amount of times. Because remember, an exponential function is a multiply function. You multiply by the same thing each time. So since we're multiplying by a fraction, when I take a number and multiply by a fraction, okay, if I take the number 10 and multiply it by 1/2, am I going to get a number smaller or bigger than 10? Smaller. And every time I multiply by 1/2, I'm going to be making it smaller still. So if your base is a fraction in between 0 and 1, it's going to be a decay function, meaning it's going to get smaller as you put in bigger values of x. So if we look at, let's stick with this 1/2 function. So 1/2 to the x. Reminder again, this is an exponent. It is not a multiply. I'm taking 1/2 and multiplying a certain number of times. So let's go ahead and let's look at this function and let's put integer values in from -3 to 3. -3, -2, -1, 0. Okay. Let's start with so here's our x's. So let's go ahead and let's start with just a 3. So here I have 1/2 to the 3rd power. So that's 1/2 times 1/2 times 1/2, which gives me 1/8. Okay, so quite small, 1/8. Okay, what about 1 to the 2nd power? That's 1/2 times 1/2. 1 times 1 is 1, 2 times 2 is 4, so that's 1/4. To the 1st power, 1/2 to the 1st, well, that's just 1/2. To the 0, 1/2 to the 0 power. If you remember from our last section, anything to the 0 power is 1. Anything to the 0 power is 1. So 1/2 to the 0 is 1. -1. Okay, so here's where we get a little more confusing. I have 1/2 to the -1. Okay, if we remember from our last section, a negative exponent takes the reciprocal. So it gives me 1 over b to the 2nd. So it takes the reciprocal. Well, if I already have a fraction, like in this case, 1/2, this negative exponent, let's rewrite that better. That negative exponent is going to take the reciprocal of 1/2, which is going to be 2 over 1, and take it to the 1st. So this negative exponent takes the reciprocal. Because if you notice, that negative exponent's gone here because I reciprocaled it. So then I just get 2 to the 1st, which is 2. So to the -1 would be 2. Oh, I don't know why that's red. Sorry. Okay, so then what about to the -2? So I'm going to go over where I have more room. 1/2 to the -2. So the negative is going to take the reciprocal. So 2 over 1. Oh, oh, excuse me. Sorry. I take that to the 2nd. So then I have 2 over 1 to the 2nd, which is 2 over 1 times 2 over 1. 2 times 2, that's 4. So to the -2 is 4. And then when I plug in a -3, that's 1/2 to the -3. Again, that negative takes the reciprocal. 2 over 1 to the 3rd. 2 over 1 times 2 over 1, which is 2 times 2 times 2 is 8. Okay. So if we go ahead, let's plot these points. Let's look to see what they look like. Okay, let's go ahead, let's graph them over here. Okay. So I'm putting in numbers from -3 to 3. So I'm going to go ahead and I'm going to just count. There's -1. I'm going to kind of go by 3s this way. Maybe we'll go by 2s. -1, -2, -3. There's 1 and 2 and 3. Okay, and I need to go up as high as 8. I think I'm going to go by 2's here. So there's 1, 2, 3, 4, 5, 6, 7, 8. So when I put in a -3, I get 8. So it's going to be way up here. Let's change that to blue. When I put in a -2, I get 4. 2, 3, 4. 1, 2, 3, 4. When I put in a -1, I get 2. When I put in a 0, I get 1. I get 1 right here. When I put in a 1, I get 1/2, which would be here. When I put in a 2, I get a 4th, which would be here. And when I put in a 3, I get 1/8, which will be here. So this function is going to look like this guy, kind of. I don't know, maybe there at the end. We'll try to do them a little better. Again, it's a curve. It's not a straight line. It does not have a slope. So basically it looks like it's just kind of the reflection of our growth. It goes down. So as I read this graph from left to right, my graph goes down. The graph goes down from left to right. So this is a decay function. Now if we talk about domain and range, domain is still all real numbers for this guy because this graph goes left and right for forever. The range is still positive numbers. The range, f of x, has to be greater than 0 because we'll still go from 0 on up. And it doesn't actually equal 0, so it does still have that asymptote. It has that asymptote at y equals 0 because it does have this horizontal line that it never actually gets to. Because as I put bigger and bigger and bigger numbers in this, I'm just going to get smaller and smaller and smaller fractions, but I'm never going to actually hit 0. Okay. So here are the graphs of 3 exponential decay functions. We have 1/2 to the x, we have 1/3 to the x, and we have 1/4 to the x. Okay, so what is the y-intercept for each of these graphs? So if we look at the y-intercept right there, right there, right there, they all look at the same spot, and it is going to be 1. The y-intercept is 1. Because anything to the 0 power, 1/2 to the 0, 1. 1/3 to the 0, 1. 1/4 to the 0 is also 1. So the y-intercept is always going to be 1. Oh, my 1 looks funny. Do any of the graphs have an x-intercept? Well, we just talked about it up here. Since it has that asymptote at y equals 0, that tells me that it has no x-intercept. It's never going to actually cross that x-axis because there's no way that it will, there's no way that I will ever actually get to a y value of 0. So what appears to be true about the domain and range values of 3 exponential growth functions? They're the same. They are the same. Domain is still all real numbers. And range is still positives. The y has to be greater than 0 because we're just going, because again, this entire graph is in quadrant 1 and 2. So it's all up here. So it's never down here. There's nothing ever down below here. So that range is just greater than 0. What happens to the value of the function as the value of x increases without bound? Okay. So make sure, I'm not sure if I talked about this enough so as x increases with, basically as x gets really big. So as x gets big. Now, if you want to shortcut that, you can say x arrow infinity. That's as x gets big. As x gets big, meaning as I put bigger and bigger numbers in, what is my output? In my graph here, as I put bigger and bigger numbers in, if I was to put in a 100, what type of value am I going to get? I'm going to get really, really small numbers. It's going to get me really, really small fractions because I'll have 1 over 2 to the 100th. I'm multiplying 2 100 times. And 1 100 times, it's going to give me 1 over 2 to the 100th, which is going to be a very, very small number. But it's not going to ever go negative, but it's going to get really close to 0. So as x gets big, the function value gets close to 0. So how we would write that, as x goes to infinity, that's saying as x gets big, f of x goes to 0. It doesn't actually equal 0, but it gets really close to 0. So here's our way of saying as x gets big, As x gets big, the function goes to 0. Okay, so what happens as x decreases without bound? So what happens as x gets small? I'm kind of out of room here, but as x gets small, meaning as we go this direction, as I put in smaller and smaller and smaller numbers, what's my function doing? It's going up, and it's going to keep going up for forever. So as x gets small, how we would write that? As x, so I'd write as x arrow negative infinity. As I go to the negative, the function what? The function gets really big. Or I would say f of x goes to infinity. It gets very big. So as these two go together. So basically it would be this all right here. Sorry, kind of squished in there. Should have left a little more room. As x goes to negative infinity, the function goes to infinity. The function gets really big. That's just saying, as x gets really small, negative, the function goes up, gets really big. And this one here is just saying, hey, as x gets really big, the function goes to 0, because that's what's happening. As I go this way, my function value gets really close to 0. As I go this way, my function value gets really big. Okay. Does the graph of each decay function have a horizontal asymptote? Well, we just discussed that. Yes. At y equals 0. It has that x-axis as that asymptote. What is the value of the base b for each of the functions? Okay, so for the first one, the base b is 1/2. So b is 1/2 for this one. For this one, b is 1/3. And for this one, b is 1/4. Which one of these decreases most slowly? Okay, so which one goes down the slowest? If we look at these, well, if we look at how steep these curves are, this one is least steep. It goes down very gradually here, so that would be the base of 1/2. So as the base gets bigger, because 1/2 is bigger, 1/2 is bigger than 1/3 and 1/4. So as the base gets bigger, then that decay gets slower. Okay, so what value of b? The 1/2. b is 1/2, decreases the slowest. Okay, so now we're going to go ahead and we're going to compare. We're going to look at this graph, and we're going to compare it to this one. Basically, what's the difference? The difference is this one's got that 3 right there. This one does not. So we're multiplying it by that 3. And so we want to look to see what's the difference. I'm going to look at the graphs of these two, and I'm going to use Desmos to do it. Okay, so here in Desmos, and I'm going to actually use function notation. Desmos is really great for function notation. What I mean by that is I can type in f of x equals, let's do that, and then parentheses 1/2, and then I use my little shift 6, my little up arrow to the x. So there's my function for 1/2 x. That's f of x. And I'm going to go g of x, name it different, 3 parentheses 1/2 to the x. So again, this x is only applying to the 3. So what's the major difference here? Okay, first of all, the major difference is f of 0 is that y-intercept. F of 0, see what's nice about function notation? I can actually type in f of 0, and it gives me what that y-intercept is, and g of 0. Okay, so that's different. If you notice, the 1 is at the point 0, 1. Let's label it. The other one is at the point 0, 3. 0, 3. Let's label that point. Okay, so there it has different y-intercepts. Okay, so we have different y-intercepts there. Again, so this blue one, they look like the blue one might decrease a little bit faster. They're still going to have the same domain and range. They still go left and right for forever. And they still only go from 0 on up. So really the main issue, the main difference is that y-intercept. What changes do you notice? What was the main difference? What was the main difference? The main difference is the y-intercept. One had a y-intercept of 1, the other one had a y-intercept of 3. Okay, so now let's do some problem solving. We got 2 problem solving problems. So we have the value of a new vehicle purchased at a price shown. Depreciates. If we don't know what the word depreciate means, goes down in value at a rate of 20% each year. What is the value of the vehicle after 8 years? Okay, This is very similar to our growth model. Do you guys remember our growth model? F of x equals a 1 plus r to the x, right? Or to the t, or to the whatever variable we use there. I used f of x here, so we'll stick with f of x. Except when it was growth, we had an addition in here because it's getting bigger. For a decay model, it's the exact same except it's 1 minus r because we're losing value. So this was our growth function. Our decay one looks just similar except it's a minus now because it's depreciating. Okay, so and A again is your initial amount. So here it says my initial amount is 18. So that's my A. My A is 18,000. Here's my R. My rate is 20%, which is 20 per 100, which is 0.20 as a decimal. So my equation becomes starting amount of 18,000. 1, since it's a decay, it's losing value. 1 minus 0.2 to the x. Again, reminder, this is an exponent, not a multiplication. You cannot divide to get rid of an exponent. Okay? But now we want to know what is its value after 8 years. So I want to figure out what is f of 8. So I take 18,000. 1 minus 0.2 is 0.80 to the 8. So I take 18,000 and I can do all of that in my calculator here. 18,000 times 0.8 to the 8. 3,019, and this is money, so 89,990 cents. This is money. Okay, so now I ask myself, does it make sense to have an 8-year-old car? When I bought it, it was worth $18,000. And now, 8 years later, it's only worth $3,000. That does make sense. That's kind of how cars work. If I buy a $50,000 pickup, it's not going to be worth $50,000 in 8 years. That's normally how it works. Okay. All right. So here's our last one. So here we have a scientist that has 360 grams of a radioactive material that has a half-life of 2 years. What that means is that every 2 years, half of it remains. Half-life is the length of time needed for half of the radioactive material to decay. How many grams of radioactive material will remain in 7 years? So we want to write a function of the form, and they even give us the form to use right here. A equals A of t equals little a times b to the t. A is the amount of the radioactive material remaining in grams, and t is the time in years. So I'm going to start by creating a table with, here's my t, time in years. So this is the years. And this is my A of t, which is my amount remaining. Okay. At time 0, I have 360 grams. Okay. It has a half-life of 2 years. So at 2 years, I have half of that. So if I have half of that, 360 divided by 2, which is 180. So I now have 180. So after another 2 years, year 4, I would have half of that. So forth and so on. Okay, so it goes down by a half each time. Okay, for each 2 years. Okay. So we now need to come up with an equation. So A of t equals A times B to the t. We know, these are my inputs again. When I input a 0, A times B to the 0, I should get out a 360. Well, B to the 0 is 1, so A times 1 equals, so I know my A value. I know my A is 360. We're halfway there. A of t equals 360 times B to the t. Okay, now I just need to figure out my missing piece. I need to figure out what B is. And we might be like, well, we multiply by a half each time, right? But my B isn't a half because I'm not going down. That's not going down by 1 year. That's going down by 2 years. So I can't, 1/2 is not going to be that B. Okay, so I need to figure out what that B is. But I know some other inputs. I know when I input a 2, So I know when I take 360 times b to the second, I get out 180. Okay, I get out 180. So if I divide both sides by 360, I know my b to the second equals 180 divided by 360, which 180 divided by 360, it goes in twice, so 1/2, 0.5, or let's write it as 1/2. 0.5 is 1/2. But that's what b to the second is. That's what b to the second is. Okay, so how do I figure out, my end goal is to figure out what b equals. Well, if b to the second is 1/2, think about it. If I know 5 to the second is 25 and 6 to the second is 36, what operation do I do to this 36 to get back to the 6? Okay, that's our square root. Okay, the square root of 36 is 6. That got me from the 30. So the square root of 49 is 7. So if I want to find what number do I take to the second power, I have to square root. So b is going to be equal to the square root of 1/2. So if I come in and I square root 1/2, let's grab my calculator. Let's take the square root, which is the button I have to hit second, x squared. So it's the button just kitty corner from the 7. And I can actually type in that fraction 1/2. The square root of 1/2 is approximately 0.707. We'll go 3 decimal places. 0.707. So I now found my base. So my equation, again, this is approximately, would be 360 times, let's put it in parentheses, 0.707 to the t, because we're using a t for my variable here. So there is my function. So I'm now going to test this function out for my points 0, 2, and 4. And we can keep going. If I go 2 more years, in 6 years, I'll have half of that. I'll have 45. Okay, so I'm going to grab my calculator and I'm going to test these. 360 times 0.707 to the 0 power is 360. If I hit the second and enter button, it brings it back again, and I can just delete that one little and say to the first. Oh, that's how much I would have after 1 year. Okay, so let's second enter. We want it to the second. Oh, we want it to the second power. I've got 179.94. Again, we rounded the 0.707. So that is around 180. That would round to 180. If I use the exact, 360 times parenthesis, the square root of 1/2, that would be the exact. Let's arrow out, put the parenthesis there, and take it to the second power. I'll get exactly 180. And instead, if I take it now to the fourth power, I would have, again, that's an approximately. If we come up and grab it and use the exact and take it to the fourth power, oh, I don't know what happened there, guys. So for some reason, it didn't go to the fourth power. To the fourth power. There we go. There gives me my 90. So if I use the exact value, or if I just copy and paste, so there's my 7.7. So if I take 360 times, if I arrow up and grab that and take it to the second power, it's a little more exact than using the 0.707, but this is our approximately, given our rounding. So sometimes it's helpful, better to write instead of equal, put approximately, because we had to do the rounding. You can't equally, there is no number, no whole number that when I take it to the second power, I get 1/2. Okay. So then it asks me to, how much radioactive material will remain in 7 years? Well, A of 7. So I take 360 times that 0.707 to the 7th power. Now, to be the most exact, I would use that exact. So I'm going to go up and grab that, hit enter. Now, instead of going to, I'm just going to go to the 7th power, I would have approximately 31.82 grams. So after 7 years, this is how many grams will be remaining. And again, you may have a rounding error because if I just use the 0.707, I'm going to be slightly off. I get 31.79. And if I round that even farther, and instead of using the 7.7, if I use the 0.71, hey, it's going to be off a little bit more. So your answers might be a few decimal places off of the book's answers, depending on whether you use the rounded or the exact. I would prefer you use the exact. You can use the exact because you're a calculator. You just copy and paste it in.